Here you go. All right, good afternoon, everybody. Right. So today we're going to be talking about finally the formation of the solar system. I went a little slow on the first lecture, took a little longer than I was expecting, but today we're finally going to talk about this. I have a question about Pluto, and I'll get to it. I'll address it. Just a reminder that homework number 1 will be posted on iLearn tonight. There is a button that says homework, and I will be posting it in a couple of hours. So in general, on Fridays, you will find it in the evening. I wrote down some recommendations of things that you should do with it, but I mean, it's just the obvious. Download it, create your own text file. Try to answer the questions based on what you remember from lecture, what you wrote on your notes. If you're not sure about some questions, then use the textbook. If you're not sure about the answers, you're welcome to work with friends, with classmates. You're welcome to discuss things online. That's fine, as long as you don't post the answers. And then you're going to bring your homework all finished to your discussion section next week, which will start meeting in person. And that's your opportunity to make absolutely sure that you got the answers right. So once you're sure, your TA will ask you to put your stuff away, and then you will take a written quiz. And it'll be 2 questions from the homework taken at random. It'll be different questions for different discussion sections, so it doesn't do you any good to ask others what questions they have on their discussion section. And then make sure you save your answers for later, because that's going to be your study guide for the midterm and for the final. So there's 2 midterms there, and then a final. The homework will have anywhere between 10 and 20 questions. The one for today should be a little shorter, maybe around 12, depending on how much we cover today in class. And is it okay if we write our answers in our notebook? If you mean the answers to the quizzes, they're actually going to hand you a piece of paper where you will be writing your answers. The homework is not multiple choice. The homework is not to be turned in. The homework is just a set of questions for you to write answers to in essay form. And yeah, so it will not be multiple choice. You can do digital notes. Yes, of course, you can take your notes any way you want. Very good. So I think that's all the questions about homework. Yeah. So yeah, so just remember, discussion sections finally start next week. The first ones should be on Tuesday, and make sure you go and in person. It's not online. So today, like I said, we're finally going to get to the planets, but just one more thing before we get into that. So last time I told you what a light year was. A light year is a unit of distance, not of time, even though it has the word year, and it's just the distance that light can travel in 1 year, right? Yeah, so I mean, you could say, you know, I mean, we could have used something else, right? Like the distance that a turtle can travel in 1 year, but it wouldn't be very long. So since light is the thing that goes the fastest and that can cover the most distance in a given amount of time, that's what we chose as a unit. And so figuring out how long it can travel, which is a really, really, really far, really large distance, that's a light year. So just for your knowledge, just so that you see that it is a very large number, 1 light year is 5.88 trillion miles, not million, not billion, but trillion miles. I do not ask you to remember that number. We will never use miles basically in this class. Just try to get it in your head that it is a huge number. And then it gets crazy because we'll be talking about tens of light years and hundreds of light years, and then millions of light years and even billions. So as we go along in this class, we will be looking at things that are farther and farther away from Earth. One thing that is interesting, right? I mean, you can use light years or light seconds or light minutes, light days. You can use any of those units. And it's just, again, how long light takes to travel from one point to another. So for example, light takes 1.29 seconds to get from Earth to Moon or from Moon to Earth. It takes 8 minutes for light to go from the sun to the Earth or vice versa. And then, here's another example, Earth to Mars, 12.7 light minutes. The nearest star to us, other than the sun, is called Proxima Centauri. Proxima Centauri is 4.3 light years away from us. And then when you talk about things that are bigger, like our galaxy, right? I told you it starts to get crazy because the other side of our galaxy, the Milky Way, is 52,000 light years away. One thing that is very unique to astronomy as a science is that we actually get to see in real time, we get to see the past. Because why can you see me? You can see me because the light that is coming from your computer or your device is traveling to your eyes, right? So that's why you can see me. In order to see anything, that image, which is light, needs to travel to your eyes, right? So when we look at the moon, tonight, I actually don't know what phase of the moon it is tonight, but if it's out and you look at the moon, the light, that image that gets to your eye has been traveling for 1.29 seconds until you saw it, which means you're seeing the moon as it was 1 second ago, 1.23 seconds ago. That's almost nothing, right? That's almost instantaneous. But when you get to something like the sun, which is farther away, then it starts to make a difference, right? We see the sun as it was 8 minutes ago. So if something happens right now in the sun, we wouldn't know. And we won't know for another 8 minutes until that information, that light, has enough time to travel to us. And then you can think, you can keep going like, okay, so then Proxima Centauri, which is 4.3 light years away, we are seeing it as it was 4 years ago, right? In that planet, so not planet, sorry. If there's a planet around that star, which there is, and if there were Martians or aliens, and they were looking at us, they would see that we are in 2017. We wouldn't even have the pandemic yet. If they had a super powerful telescope and they were looking at us, there would be no pandemic. Nobody would be wearing masks. Trump would be president of here. In Mexico, it would be a different president too. Like it would be a different world because it's 4 years ago. So it is a little bit of a crazy thing. And in astronomy, we take advantage of this because then we can see the universe as it was before. And this might give you an idea of why we want to use very, very powerful telescopes. Well, because then we can see very, very, very far away, which also means very far in the past. So we have a big advantage over archaeologists. Archaeologists also want to know what happened in the past, but they have to dig and they have to try to figure out, connect the dots. We don't have to do that. We can just see it. We can see what was happening in the past, which is super cool. Right, so yeah, so I'm getting questions about the sun, right? If something happened to the sun, if there was like a big explode. It's not going to explode. The sun is not going to explode, but it does have some explosions, which we'll talk about later. And it's true. We don't get to see them immediately. We have to wait like 8 minutes until we actually see them. If a star exploded, we wouldn't have a clue for a while, depending on how far it is. That's right. So a lot of questions that are similar. Very good. So we will come back to this, but just keep in mind, things in astronomy are measured in light years in general. And then we can see in the past. So yeah, so question. So every time that we look up, we're looking at the past. Yep, that's right. Very good. So finally, we get to the solar system. So like everything else from now on to the end of the quarter, we're going to try to be focusing on the violent things that happen in the universe. And so we're going to see the violence in the solar system, in the sun, in the solar system, violence in stars when they explode, violence in galaxies when they collide, and so on. But in order to talk about, like the gory stuff, we need to learn some things about the different aspects of the universe that we will be talking about. So we will begin with the solar system. And the goal here is to learn, about cataclysmic events, like when an asteroid collides with a planet, things that can cause global extinction, for example. So we will get to that, but in the next couple of classes, we will talk about the solar system and how it was formed. So for the rest of this class, I'll just tell you about some properties of the solar system, and then we'll get to how it was formed. Before we get to that, I do want to clarify something. A lot of people get the words solar system and galaxy confused. So I want to settle that for, once and for all. And let me do a poll here. So which one is bigger, a solar system or a galaxy? So let me launch this poll. And which one is bigger, solar system or a galaxy? All right. Okay. All right, very good. So very good. The vast majority of you said galaxy, and that is the correct answer. Galaxy is much, 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 much bigger than a solar system. Solar system is what's our star, the sun, and the planets, as pictured here. So the planets and asteroids and comets and everything that is in close proximity to the sun. That's a very, very small thing compared to a galaxy, which is pictured on this side here. So each one of those little dots, those bright dots that you see that make up this galaxy, is a star like the sun. So if you were to plot or to draw the solar system to scale in this galaxy, you wouldn't even be able to see it. I want to make this distinction. They're not the same. Solar system and galaxy are not the same. One is pretty small. It's made of one star. The other one is very big, the galaxy, and it's made of many stars, millions of stars, sometimes billions of stars. So they are very different. And is the solar system part of a galaxy? Yes, the solar system is one star with planets around it. And it is part of a galaxy called the Milky Way, which we will talk about later. And it's made of many stars. So in fact, here it shows you are here. Obviously, this is not the picture of our galaxy. It's another galaxy. But if this were a galaxy, that's about where we would be, the solar system. I sometimes teach some seminars to teachers, right, to middle school teachers, and I hear them making this mistake a lot. And they say galaxy instead of solar system and vice versa. So that's why I want to make it absolutely sure that we're all clear on this. Besides this, there's another term, universe, right? Universe is everything that we have access to, right? Everything, like all the stars, all the galaxies, all the planetary systems, everything that we can observe with a telescope, that's the universe. So, and maybe even more than that. So that's the biggest, right? Solar system, the smallest, universe, the biggest. Very good. Does every star have planets? We will get to that. A lot of them do. That's the short answer. All right, in our solar system, planets are very tiny compared to the distances in between them. So whenever you look at a textbook or a picture on the internet of our solar system, you'll see the sun in the center, and then around the orbits of the planets, and the inner planets and the outer planets, and you see the big planets, right? But actually, if they were drawn to scale, you wouldn't be able to see the planets. It's mostly empty space. And I wanted to give you a sense of what that is like. So as part of your homework, one of the questions is asking you to watch a 7-minute video, The Solar System to Scale, where somebody gets frustrated with the idea that he can't find a solar system drawn to scale. So then he and his friends go and draw their own, right? And they have to go to the desert. And I like this video because it really gives you this sense of how small the planets are compared to the space in between them, and how vast the distances in the universe are. So this will be part of your assignment. You'll have to answer a couple of questions regarding the video. And I'm asking the TAs not to give you the answer because I want to make sure that everybody watches it. All right, so let me tell you a few properties. I mean, there are many different properties of our solar system. I'm just going to focus on 3 of them that seem to be just interesting, because why does the solar system why does it look this way instead of some other way, right? So let me tell you about them. The first property that astronomers have observed for a very long time and kind of scratched their heads about why this is that the sun, the planets, and just about every large moon, satellites seem to rotate and orbit in an organized way, right? All of the planets go in the same direction. They're all on a plane. The orbits are not random. They're actually all lined up. Most of the planets rotate in that same direction, and the moons orbit the planets in the same direction, and they also go in the same direction. And we kind of take it for granted because we've grown up seeing images like this, cartoons like this, and we take it for granted. But why should that be? Why should they all be lined up? Like, who told them to line up? Who told them to be on the same plane and to rotate in the same direction, right? So this is something that if you're going to come up with an idea of how the solar system was formed, you need to be able to explain this. What caused this to happen? And somebody's asking, gravity. Gravity is definitely a big player in this. Gravity causes the solar system to form, and we'll talk more about that. But gravity wouldn't necessarily make everything go in the same direction. So let's keep this in mind. Second property that has, scientists scratching their head. I mean, in the past, we seem to know why now. But there's two very distinct type of planets. There are terrestrial planets, which are close to the sun. So here's, again, the sun in the center, and then 4 planets in the center, Mercury, Venus, Earth, and Mars. They're small, they're rocky, and they're close to the sun. And then 4 other planets that are completely different. And they're big, they're gas rich, they're not rocky, they're not small, and they're far away from the sun. So that's Jupiter, Saturn, Uranus, and Neptune. And somebody was asking about Pluto. Maybe I'll get to that after I explain. So Pluto is no longer a planet. You guys probably are at an age where Pluto was never a planet when you were in school. I can't figure it out. Yeah, probably. I mean, by the time you got to school, Pluto was not considered a planet anymore. So we'll talk about that. Anyways, the terrestrial planets, which the Earth is part of those, like I said, they're closer to the sun. They're smaller in size and in mass. The Jovian planets, in contrast, are a lot bigger, much bigger, like 11 times, like, 15 times bigger than the terrestrial planets. So terrestrial planets are much higher density, right? Density is just the amount of mass or matter in a given volume, right? So high density, for example, if you compare, let's say a bagel to Wonder Bread, right? Wonder Bread is light and fluffy. There's not a lot of bread in a given amount of space, whereas a bagel is like pretty dense. So high density, a bagel, low density, Wonder Bread. In the same way, terrestrial planets are high density. There's a lot of mass compacted in a very small amount of space. Whereas the Jovian planets, I mean, they're much bigger, more massive altogether, but a lot fluffier, right? They're a lot less dense. Terrestrial planets are made mostly of mostly of metal and rocks, whereas the Jovian planets are hydrogen, helium, and hydrogen compounds. Terrestrial planets have a solid surface, right? We can land and we can walk on the surface of Earth. Jovian planets, you can plunge in the Jovian planet like Jupiter, and then you would be flying for a very, very long time. Eventually you would hit something solid, at the very core, there's something solid, but it's not like a surface like the Earth. Not the same type of thing. What does it mean by no solid surface? Yeah, what I just said. So the terrestrial planets have very few moons. The Earth has 1. Venus and Mercury don't have any. And then Mars has 2 little rocks that go around it. So it's not exactly a moon, right? They're just 2 little like asteroids almost. Whereas the Jovian planets, they have tons of moons, right? I actually don't remember how many, like 60 something, some of them are like, the count is over 100. So they have a lot of moons and they have rings. We are used to thinking of Saturn as being the planet with rings, but in fact, all of the Jovian planets have rings. It's just that they're very faint and you can't see them with your eye. But if you take long exposures, pictures with the Hubble Space Telescope, for example, you can see rings in all of them. All right, so so I'm getting a lot of questions, then I think I will be answering most of them as we go along. And thank you, Jacob. So Jupiter has 64 moons, so lots and lots of them. Could I repeat which planets are terrestrial and which ones are what do you call that? Jovian, right? So, well, let me turn that question to you. If you remember the order of the planets, the 4 that are closest to the sun are the terrestrial planets, and the 4 that are farther away from the sun are the Jovian planets. So let me ask you guys this question. So which of these planets are Jovian? So which of these planets are Jovian? And you should check all that. Oh, does it say? I messed up. So sorry about that. Single choice. I messed up the type of poll. I should have, it's supposed to be a multiple choice and I did a single choice. So sorry about that. I mean, pick one, pick a Jovian planet and then we'll see. Yeah, sorry about that. All right. Okay, so let me go through them. Jovian planets. So Jupiter is one Jovian planet. In fact, all of the others are named after Jupiter because Jupiter is the name in Latin is like Jovian. Uranus is another Jovian planet, Saturn and Neptune. That's correct. So sorry about the messed up poll. All right, so again, terrestrial planets, Earth, Mercury, Venus, Earth, and Mars, Jovian planets, Jupiter, Saturn, Uranus, and Neptune. All right, so the third property that I wanted to talk about is that besides these big planets that there are, and the two types of planets, there's a bunch of smaller stuff that seem to be concentrated in certain parts of the solar system. So we have asteroids, which are mostly concentrated between the orbits of Jupiter and Mars. So sort of in between the terrestrial and the Jovian planets. And they are rocky. They look like this. They're made of rock. And then much farther away, so beyond the orbit of Neptune or around Neptune, we have a different type of object, which are comets. And the comets, when they come close to Earth, this is what they look like. But when they're farther away from Earth, they just look more or less like an asteroid, but with ice. They look icy. So they seem to be concentrated in specific parts, and there's just a lot of them. So there's a huge number, right? Like hundreds of thousands of them. And they're not planets. And if you put the mass of all of them together, they wouldn't even make a planet, or maybe they would make a small one. But they're very numerous, very small, very different from the planets. So let me summarize the three things. So one, large bodies have orderly motions. Two, there are two different types of planets, small rocky terrestrial planets and large hydrogen-rich Jovian planets. And three, there is a swarm of asteroids and comets that exist in certain regions of the solar system. Let me pause for a second. So I use the word hydrogen, which just to remind you, hydrogen is a gas. It is the absolute lightest element in the periodic table. So it's the simplest element of all. And it is a gas. After hydrogen comes helium in the periodic table, which is also a very light gas. And later on, we'll talk more about gases and the periodic table. But just now, keep that in mind. Hydrogen is a very light gas. It's very abundant in the universe, and so is helium. So these planets, the Jovian planets, are very rich in hydrogen and very rich in helium as well. All right, so those are three properties that, like I said, there are other properties, but we're going to focus on these three and ask if we were to come up with a theory that explains how the solar system formed, how would that theory explain these three properties, right? So let me just back up for a second. And, you guys grew up knowing that there are planets around other stars. Or, some of you don't know, and that's fine. But some of you have heard that there's planets around other stars, that our solar system is not the only planetary system. And, we all, even I grew up watching Star Wars and Tatooine. And
就老太就死老太，但是老大爷就不能骂死老大爷。
All right, thank you. So even I grew up thinking about Star Wars and Tatooine and all these different planetary systems, and now watching The Mandalorian and all these other planets. But 25 years ago, the world didn't know that there were other planets around other stars. And so all we had was our solar system. And if we wanted to know how it formed, we could only think of the properties of our own solar system. Now we can look at the properties of other systems, other planetary systems, but before we couldn't. So when they came up with a theory that explained how the solar system formed, they could only consider these properties, the ones that we mentioned. So what's the theory that astronomers came up with? And so it is called the nebular theory. Nebula is just cloud. I mean, and this is just comes from the Latin, that means cloud. And a nebula in the context of astronomy is just a cloud of gas in space. So the nebular theory says that the solar system formed from a giant cloud of interstellar gas. What is interstellar, besides the movie that came out almost a decade ago, right? Interstellar just means in between stars, right? Inter, in between, stellar, star. So gas and dust that was in between stars, interstellar gas. So this theory, and in a few weeks, we'll talk about how stars in general form, and we'll see that they all follow this same idea. And again, nowadays we can actually observe them when they're forming, but back then we didn't have the technology to do that. So the idea is, let me go back. The idea is this is an actual nebula. This is a cloud of gas in space. The idea is that gravity caused it to shrink in size. Gravity is an attractive force. And so anything that has mass, such as a cloud, will have attraction, will have gravity. So again, in a few weeks, we'll talk about what are the specific conditions that lead to a cloud collapse. But for now, let's just take it for granted. So a cloud of gas collapsed because of its own gravity. And because that cloud of gas was spinning a little bit to begin with, right? Like a little bit like in this picture. There's a little bit of motion of the gas, but as it began to shrink because of the force of gravity, as we learned last week, or no, last class, I think, because of the conservation of angular momentum, that spin that was there to begin with is conserved. Sorry, so if you remember, angular momentum is just the radius times the velocity times the mass. So the mass of the cloud, which as it shrinks, it's conserved, but then the velocity, it was spinning a little bit, and as it shrinks, it starts to spin faster and faster and faster because of conservation of angular momentum. So let me ask you a couple of questions. Again, taking for granted that a cloud of gas shrinks because of gravity. So the question, why did it spin faster? And then the other question, so it'll be a 2-question poll. The other one is, which of these quantities change as the solar nebula shrank? So let me launch it. So now one is a single choice, the other one is multiple choice. And let me read your questions while you guys do this. So. All right, so there's some really good questions. I don't want to go too far off topic. So I'm only going to answer the ones that are closest to the lecture. And then if you stay behind at the end, I can answer the others. So let me end the poll and talk about the answers. So first, as the cloud of gas and dust shrank, why did it spin faster? It's because of conservation of angular momentum. And you guys are right. It is because its radius became smaller, right? One quantity became smaller. So in order to keep the angular momentum the same, then another quantity has to go up, right? Radius goes down, then velocity has to go up. And so that's why it spins faster and faster. Which of these quantities change as the solar nebula shrank? Mass didn't change. I mean, if you get really picky, then yes, there could be some small changes in mass, but really mass is staying the same. It's becoming smaller, but it's not getting rid of mass. It's the same amount of mass. And the analogy that I'll keep making is Wonder Bread, right? You can have a big piece of Wonder Bread, and then if you squeeze it, you can make it into a very small ball. That ball has the same amount of mass as the slice of Wonder Bread, right? But it's very dense. So it's the density changes, right? And so density was one of the correct answers, because as the nebula shrinks, it becomes denser and denser. So the density increases, but the mass stays the same. Angular momentum, oh no. So most of you answer angular momentum, and that is the one answer that is absolutely wrong. Because conservation of angular momentum means angular momentum does not change. So angular momentum is the thing that doesn't change, right? So which of these quantities change? Not angular momentum. Okay, so that's very wrong. And I failed at explaining conservation of angular momentum. Conservation just means something doesn't change. Conservation of momentum means that the momentum doesn't change. Conservation of mass means that mass doesn't change. Any conservation that you hear, it means it doesn't change. Volume, of course, volume changed, so that's correct. And that's what the minority of you answered. Volume, because it's becoming smaller. Volume is just the size of something, right? All right, very good. I failed. So for question 2, the answer is density and volume. Those are the ones that change as the nebula shrink. And for question 1, the answer is the cloud spins faster because its radius became smaller. Can I remind you of the relationships between density and volume? Yeah, so, well, I mean, we'll talk about that, but it's just mass over volume, right? Density is equal to mass over volume. So if that's what you were going after. All right, so a few of you are actually asking me about black holes, and we will get to black holes. I promise we'll talk about black holes for an entire week, but I'm going to skip that for now. All right, so as the cloud spins faster and faster, it flattens into a disk. And the principle is very similar to how you get a pizza pie. And I don't know if you guys have ever seen, I mean, if you go to places like Blaze, they cheat because they put the dough and then they just, squeeze it. But what I'm showing here is like the original way to make a pizza pie. And the way is you take the dough and you start spinning it. And because you spin it fast, and again, because of angular momentum, it flattens and it'll become thinner and thinner. And this is what happens to the cloud of gas as it collapses in order to form the solar system. As it collapses, it starts to spin faster and faster, and then it flattens into a disk. And so just like that, pizza pie, our solar system or our nebula, our solar nebula becomes a flat tortilla or a flat pie, right? So the disk ends up rotating in the same direction as the nebula, but just faster. And again, because of conservation of angular momentum. And then here's what will answer many of the properties, right? What will explain many of the properties of our solar system. The planets form from the material inside the disk. So then eventually, and next Monday, we'll talk about the exact process of how this happens, but the planets form within the disk. And of course, they end up moving in the same direction, right? Because they form from material that is moving around the sun. So planets inherit their motion from the disk. So they all rotate in the same direction. What is the distinction between the disk and the nebula? The nebula becomes a disk, right? I mean, this is a disk of a nebula. It's just a flattened, rotating, much smaller nebula that eventually will become planets. All right, so we can go back to the questions or to the properties. So the first one, that large bodies have orderly motion. So why? How does this theory explain that large bodies have orderly motions? So in the theory, in the nebular theory, again, it's a very large cloud of gas. It shrinks, it becomes, it starts spinning faster as it shrinks. And because it starts spinning so fast, it flattens into a disk. From this disk, in the very center, the sun forms. And by the way, those of you, which are many, who are asking me, why doesn't it just become a black hole? Because the sun is formed and the sun gets pretty hot, and that pushes out against gravity. So gravity doesn't make it collapse into a black hole. But we'll get to that later, I promise. Sun forms in the very center, and then the planets form in the disk that is rotating around. So this explains a lot of things. All planets end up lying in one plane, which is the plane of the disk. All planets orbit in one direction, right? Again, the direction of the spin of the disk. The sun rotates in the same direction, right? Everything is rotating. Planets tend to rotate in that same direction. Most of the moons orbit in this direction, and most of the orbits are nearly circular. I didn't really get into that in detail, but the idea, I mean, if you think about a planet going around, or not a planet, but debris going around a star, if anything tried to move in a different, not in a circular direction, it'll probably collide with the rest of the stuff which is going in a circular direction. And so the orbits end up being pretty circular just because of the collisions. All right, so Very good. So I have some great questions. So why do some planets move in opposite direction? That's right. So the solar theory doesn't explain why, for example, Venus rotates. I mean, it's going orbiting with everyone else, but it's actually rotating in the opposite direction. So we have to figure out, is this something that can be explained in some other way? Or is it something that discounts the entire theory? And I'll get to that later. But it is important to see, like, there are some things that are not explained. Some of you are asking, how come planets don't form flat like the solar nebula did? So I will explain that next time when I explain how planets come to be, right? Because the process is a little bit different. The process of how planets form is not just a nebula rotating very fast. It takes some building blocks, so we'll get to that. Can I elaborate on the idea that the planets are formed? Yes, that's actually, let me get to it, because you guys are asking a lot of questions about that. So the next question is, why are there two types of planets? So let me actually show you a video that will give you a very general picture of how planets are formed. And then next class, we'll start talking about the details. And so let me play that video, and then we'll end the class.
It's a dance that lasts millions. It's a dance that lasts millions of years. It starts when the gas and dust form microscopic clumps, and it ends with new worlds. As the clumps get bigger, they start to stick together too. They form clumps of clumps, always bigger, always heavier, all swirling around each other. And at the center of them all, a vast cloud of gas and dust takes shape. A whirling ball of matter, sucking in everything. It grows bigger and bigger, hotter and hotter, until a new generation of stars is born. And this one is our sun. The remaining gas and dust is blown away, leaving behind the planets. They keep growing. Smaller lumps of rock fall onto them for millions more years. And when it's over, a new world is revealed. Our world, the Earth. But if that's how the Earth